So we are once again back to the refractors. In refractors, we know that these are the lenses which we use to see an object. And while using these lenses, if you have already done that, you must have seen that whenever you see an object, you find a kind of a rainbow around that object, a color around those objects. And that's the problem with the lenses, what we call the spherical and chromatic aberration. And that comes in the main lens, the main objective lens. So what we do is to make an achromat lens in which we use a positive and a negative lens of a different material, as you can see in the figure, and correct the aberration there. And as I told you, the lenses are thicker in the center and thinner at the edges, and glass being a very viscous liquid, we cannot make very large telescopes out of these lenses, because at the edge, when the lens is thin, where the lens is thin, it will always flow after, let's say, after a few years. So the world's biggest telescope in the refractors we have in the Yerkes Observatory, that is around 40 inches in diameter, and the biggest single mirror we have 6 meter plus. So you can imagine the advantage they have in case of reflectors. But refractors give us a perfect image because there is no obstruction in between, as in case of the reflectors. So if your telescope is small, then go for a refractor, and if you want to make a big telescope, go for a reflector. In case of the reflector, we have the light coming onto the mirror and getting reflected back, goes back to the focus, and from there we have a secondary mirror, because if we don't put the secondary mirror, if we try to see the object, we will see our own face over there. So to remove that problem, what we do is we put a small flat mirror in front of the reflecting mirror, and we see the object 90 degrees to the angle where the object is exactly is. So initially it looks very odd that you are pointing your telescope somewhere there and seeing the object somewhere else. But in case of reflectors, we do away with the problem of the achromatic aberration. But then we have other problems here. If I want to make a telescope very small, then there's a problem of spherical aberration. I have to make it a parabola, and so many other things. But a basic reflecting telescope gives you a parabolic mirror and a small flat mirror to start with. And then there's a third kind of a telescope, which we call the catadioptric lens mirror telescope, in which I use both mirror and the lens combination. You can see in the figure that at the entry of the light, where the light enters, we have a correcting plate, and we have a mirror at the back, reflecting mirror at the back, which has a hole in it. So that mirror is a spherical mirror. The correcting plate in the front corrects it for the parabola, and then the light goes back to the focus once again, where a flat 45 degree angle mirror should have been there, but because we are using this catadioptric as a folded optics, so at the back of the correcting plate we have coated it to make it a hyperbolic reflector secondary mirror, which reflects the image back to the mirror, and it goes through the hole at the end of the eyepiece. You see the image. So it's a folded optics. If you have, let's say, mirror of 2 meter focal length or 3 meter focal length, the tube would be very small. Tube can be, it's around half a meter or 0.6 meter length. So that's the beauty of this telescope, that it's a highly portable telescope, because for a longer focal length, the length of the tube is very small. Now when we say telescopes, we had skipped the thing which comes in between the telescope and the naked eye view. That's the binocular, because telescope will always give you a view which is half to 1 degree, and that's like finding needle in a haystack if you are looking at any of the objects in the sky. The binoculars give you a very wide field of view. They give you around something around a normal pair of binoculars will give you 7 to 8 degrees field of view. So if you are graduating from the naked eye level, you just first go to the binoculars and then go for a telescope. But the problem with the binoculars is that they are without the stand, most of them, and the eyepiece has got a fixed focal length. By fixed focal length, I mean the magnification in the binocular would be simply a fixed one. If it says 10 by 50, 10x50, so 10 is the magnification and 50 is the aperture of the binocular in terms of mm. But these binocular gives you very good field of view. They give you a sense of three-dimensional viewing. Try looking at the moon through a telescope and through a binocular. You will know the difference. Now, when we look through a binocular, what kind of a thing we see? In the bottom of the image, you see different magnifications over there. There is a person surfing in the sea. 1x means the naked eye towards the left hand corner. Then I have the 7x with the binocular. You can barely see that person surfing on the wave. And if I come to the 20x, you can clearly see that fellow with the zoom thing. It's like seeing a match with the naked eye and having a binocular and seeing only the stumps or the, let's say, the gloves of the player. So that means more the magnification, less the field of view, and more the field of view, less the magnification. Now then why we use telescope? Because if a binocular gives me a 20x power, and what will happen with the same power, same magnification with a bigger telescope? The difference is in terms of the resolution. The bigger the mirror is, the more better it will be to resolve 2 points into the space. In this figure over here, you can see 20 by 50 binoculars at 20x and 100 mm telescope with the 20x thing, and you can see it's more clear in the 20x in terms of the telescope because we have got bigger dimension in the terms of the mirror. Now if you have a 20x in one of the largest mirrors in the world, they will show you the same size of the image, but the clarity of the image would be much better in terms of resolution in bigger mirrors. Now here we have some of the objects which one can see with a 3-inch telescope. You can see the M13 globular cluster as a fuzzy patch, but if you see that thing through a 6-inch telescope, then it will become more clear, and if you see it through a 12-inch, then you can see the individual stars over there. Same is the case of the Saturn over there. With the 3-inch it looks like a blob with the ears around it. Then a 6-inch telescope will clearly show the rings, and a 12-inch at the same magnification will show you so many rings over there. And on the right hand side you can see the moon at 30x magnification, at 100x, and at the 250x in the same area. So you can see what is what you can see with different sets of telescopes.